So before I start, I want to say thanks to Dario for inviting me a second time to talk in this meetup. And I hope you will all enjoy it. My name is Dimos, and I'm currently working at a company called R3, where I'm helping build a distributed ledger platform called Corda. And today I'm going to talk about shared nothing architectures and where to find them. But before we go there, I would like to first have a look back at the birth of the microservices movement and some of the main driving factors behind it. So in this slide, we're looking at the canonical example that I'm sure all of you have seen 1,000 times at this point, which is essentially an e-commerce application that has several different modules that implement different business functionalities, such as ordering, billing, user accounts, etc., etc. And they're all deployed as a single artifact. And they store their data in a single shared database in different tables in it. And then eventually this whole application is transitioned to a microservices architecture where each one of those modules is split outside to a separate service. Every service now has their own private data store. And the services do not have any access to the data stores of other services, and they can only communicate through remote procedural calls. And each service is trying to give a clean interface to the other services. And there are many benefits from this architecture that many people talk about. Here we'll focus on two of them that are quite commonly cited, and they are related to this talk. The first benefit is the fact that people now are able to have increased agility and faster feedback cycles when developing software. And the main reason for that is teams don't have to communicate that much anymore. They can work on their own service independently, as far as they don't break their customers, the other services. So if, for example, they want to change implementation details of the service without changing the interface at all, they can do these changes and deploy them independently without any coordination. The second benefit that is often cited is the fact that we are now able, by splitting this system into different parts, we are able to deploy these services independently, and we can also scale them independently. And this is useful because we might have different services having different requirements. So some of the services might have very high load because they're user visible services, like those used for ordering, for example, or for displaying product pages. But other services might not have that much traffic. For example, there could be services that are only used for internal purposes by internal administrators or internal employees. And so we can scale them accordingly. And these two benefits might look a bit different, but they have a common element under the hood, which is they're all derived from a reduction in sharing, essentially. On the one hand, when talking about increased agility and faster, smaller feedback cycles, the sharing that is reduced is essentially a sharing in an organizational aspect. So as I mentioned before, all these teams don't need to communicate that much. So there is less sharing there and less communication overhead. When looking at the second benefit, the sharing we're talking about has more of a technical meaning, because it is about how resources are essentially used, right? Services use separate physical resources now, and this gives us this nice independence in terms of deploying them and scaling them as well. And the reason we're looking at this essentially is because this movement to the microservices architecture and in general similar architectural patterns also accelerated the adoption of shared nothing architectures. We'll look later. And the concept of a shared nothing architecture is not new, really. It's quite old. So this is one of the original papers that made the case for this architectural pattern. And it was published back in 1985. And it made the case for the shared nothing architecture by putting it in contrast with two other patterns. The one is known as the shared disk architecture, and the other one is known as the shared memory architecture. The shared disk architecture is one where we have multiple different processors, each one with their own private memory space, and they all share a common array of disks. A shared memory architecture is one where we have all those multiple processors and they all share a common memory space as well. And then we have the shared nothing architecture that we will look at here, where these processors do not share anything. They don't share either memory or peripheral storage. And I'm talking about processors, and some of you might be thinking, what does a processor really mean here? And of course, it can mean many different things, right? It can mean a thread, it can mean a Docker machine, it can mean a physical machine, it can mean many different things. We'll try to keep it abstract here. And let's say that we live in a very simple world where everything is just a single physical server, and a processor is just that server. So we're not talking about virtualized architectures or anything like that. We'll try to keep it very simple. And before we move on to the actual examples, first I would like to talk about a few principles that are common across all the examples we look at, more or less, and some of the benefits that come from these principles and also some drawbacks. And then as we move through the examples, hopefully you'll be able to relate to these points that we'll talk about here. Shared nothing architectures are based mostly on the technique of partitioning. And partitioning is essentially the process of splitting a dataset into smaller datasets, and then delegating the responsibility of storing these datasets and providing access to these datasets to different parts of a system. Of course, if we're talking about a stateless system that doesn't have any state, instead of a dataset, we can replace that with a workload. So we can have a workload from other systems or from customers. And then what we can do is we can split this workload into separate independent workloads and then distribute those to different parts of the system. So this technique is at the center of these architectures, and it essentially helps us reduce sharing by doing this splitting. And it can also give several benefits. These are the main three benefits. The first one is scalability, because by splitting a system into multiple independent subsystems, we can scale it more easily. And the way to do that is we can just create more partitions and give more resources, provision more servers. And this technique of scaling is known as horizontal scaling, because we essentially scale the system by adding new resources, new servers. And it comes in contrast with another technique which is known as vertical scaling, where instead of adding new resources, we essentially replace the existing resources with more powerful ones. So we can get a more beefy server, for example. So the shared nothing architectures leverage mostly horizontal scaling. And this form of scaling is, first of all, more cost efficient, typically, especially in large scale systems. and is also less subject to limitations of physical hardware. When you scale something vertically, you might reach some limits, after which you can find a stronger and more powerful machine. The second benefit is performance, and this we have this benefit because, again, as we split the system into multiple subsystems, requests can go to each one of those partitions, and they can be handled only by this part of the system. And so we have less contention and interference between these different parts of the system, the different partitions. And this means we can have, first of all, higher performance because of this. The more partitions we have, we can create, we can split the workload and the data sets more uniformly. And we can also have more consistent performance, assuming we do that properly. So assuming we have a nice distribution of the data and the requests are uniformly distributed on the various servers, we can have very consistent performance. The third example we look at, and better performance can either mean lower latency or higher throughput, depending on the occasion. So the third benefit mentioned here is fault tolerance, and this is because we have all these different partitions, and if one of them fails, the other partitions can keep working. And so we don't have a full failure of the system. And essentially what we've done is we reduce the blast radius of a failure. So one failure does not bring the whole system down, but only impacts a specific part of the system. Of course, the technique of partitioning comes with some drawbacks, some limitations. The most common one is in order to achieve all these benefits, we partition the data sets or the workloads, and then we need to keep these workloads separate. So typically what we do is we do not allow a lot of capabilities across these partitions. We'll look at some examples later on. And this means from a developer perspective or from a user perspective, there are some things that might be hard to do or impossible. And in order to do those things, usually some systems select to provide these capabilities. But in order to do that, they typically have to introduce coordination back to the system, coordination and sharing between those partitions, as we will see later on. And of course, this introduction of coordination and sharing back to the system can have negative impact on all the dimensions we talked about: scalability, performance, and fault tolerance. So the first example we will look at is load balancing. And it's one of the first problems an application has to solve, essentially, in order to scale to a larger volume of clients. There are many different ways to solve this problem. Here we will look at one of them, which is arguably the simplest one and also the most widely adopted one, let's say. So starting from the bottom of the slide and going one layer at a time, at the bottom we can see we have a set of application servers that will eventually receive the request from the clients, process the requests, and then return the responses back. A layer above that, we have a set of load balancers that will be the first entry point for user requests, and then will be responsible for delegating these requests to the various application servers. And there are many different strategies and algorithms on how this distribution will work, such as a round robin or selecting the application server with the smallest number of connections or active requests or other strategies. And lastly, the clients also need a way to discover all these load balancers. And one of the common ways to do that is through the use of the DNS system. So we assign a single domain name to the whole application, and then we map this domain name to multiple IP addresses, each one corresponding to one of the load balancers. And the client is responsible for distributing requests across the different IP addresses in a round-robin fashion, for example. At this point, one might ask, of course, this box there, this big box with the DNS system, looks like a centralized shared part. So isn't that like a single central point of failure? Or doesn't it have negative impact on everything we discussed? And if you go there and look into detail on how DNS is structured, interestingly, it is also based on a shared nothing architecture. So this is composed of layers, and each one of those layers is also partitioned into different segments. So requests from clients for different domains can potentially go into different parts, into different partitions of this overall system. So it gets all of those benefits as well. So I won't go into more detail here, but DNS is an interesting case study for this architectural pattern. The second example we look at is distributed data stores. What we looked at before, we assumed it was just a stateless application. There was no state. But of course, any application that has some business use needs to manage some data at some point. And a common approach is to split the stateful part of an application from the stateless part. And the main benefit from that is those two parts have quite different characteristics. So it's useful to separate them. For example, the stateless part of an application, it's much easier to evolve. For example, you can, if you introduce a regression or a bug, you can quickly roll back the change. And there is no big deal usually. But it's trickier when you're talking about the stateful part, because there you might have changed data or corrupt data. And so regressions there are much more dangerous, and people typically have stricter operational procedures and change management processes. So we looked at the stateless part, and if we split things, then how do you do the stateful part? In order to reinvent the wheel, what you can do is use one of the data stores that are out there. There are so many of them by this point. I won't go into mentioning them one by one. But the interesting thing is almost like the majority of them follow similar architectural patterns. So what we will look at here applies to almost all of them. So that's useful. That's still useful. What they do, these data stores, is they, as we said, they split the whole data set into smaller data sets that we call partitions. And then they assign the storage of each partition to a different server, to a different physical machine. And thanks to that, as we said, they can get extremely high performance and also very consistent performance. So some of the data stores can provide even single-digit millisecond latency for extremely high traffic. But of course, if it was only one server that was storing the data for every partition, you would have a problem, because if that server was down, the partition would become unavailable. Of course, the rest of the system would keep functioning, as we said, but it's still problematic. So what most of the data stores do is they store the data for every partition to multiple servers, not just one. But then that means they need to have a way to, every time they need to update the data for a partition, all these servers that store the data, they need to coordinate with each other before making the update to ensure the data will be consistent. And they won't diverge, essentially. And there are different ways to do that. There are different algorithms and protocols, but one of the well-known algorithms, category of algorithms or protocols, is known as consensus protocols, because they help the servers come into consensus about an update operation and the state of the partition. And typically, this is what is used. So you might have heard Raft, for example, or Paxos. And so we have a list of different partitions, and every partition is stored in a number of servers. Here we have 3 servers, for example. That is called the consensus group, essentially. And this is almost the whole story about data stores. Of course, as I said, there are data stores that elect to only provide very simple operations. For example, some of them only provide key value access. You can only access, for example, only a specific item at a time, write one item or get one item. And this is what gives them extreme performance and fault tolerance. Other data stores choose to provide more elaborate operations. For example, you can access multiple items, or you can also do operations across partitions. Some data stores even decide to give transactional guarantees for operations across partitions. And to do that, they need, of course, as I said, to introduce coordination. So one well-known protocol for that is known as the two-phase commit for doing transactions across different partitions. And to illustrate what I said before, if you use, for example, two-phase commit, and one of the partitions becomes unavailable, then this might mean that any other partition that has an active transaction with this partition will also become unavailable. So we introduced some coordination across partitions, and this created a drop in fault tolerance. So the next example we look at is distributed event logs. So we looked at how applications can store data and also process data, but there are cases where applications want to transfer data between each other. And typically this is done either through a message queue or an event log. And Kafka, of course, is the most popular of them. So Stathis made a whole presentation out of it, so he did my job, essentially. And so I won't go into a lot of detail here, but we'll look at the high-level architecture. And interestingly, it doesn't differ that much from what we saw when talking about distributed data stores. All the events are essentially split into different partitions. And then each one of those partitions is stored in a set of servers that are called brokers in this case. And they essentially form kind of like a consensus group, as we said before. And then at the top, we have the producer application that essentially sends events that can go to different partitions. And at the bottom, we have consumer applications that pick up events potentially from different partitions. An interesting thing to note here is one decision Kafka has made, for example, is to provide ordering guarantees only for a single partition. So the order in which events are emitted to the event log will be picked up in the same order by consumers, but that only applies for a single partition. And this allows Kafka to avoid doing any coordination between partitions and to have all these benefits that I described about. So this is also a case of reducing sharing and coordination. The last example we look at today is that of distributed data processing frameworks. So as your application becomes more and more useful and gains traction, you get a lot of data, and then you need at some point, to analyze that data to understand how the users use your product and how you can improve it. And it gets more challenging the larger volume of data you need to use. So the more successful your application becomes. It can get up to terabytes or petabytes of data. So when you reach that volume, you need to use some form of distributed data processing. And what we're looking at here is one of those frameworks called Apache Spark. This is typically deployed on top of a distributed file system as well. And the most common deployments have HDFS as that file system. So this is an example of a deployment we're looking at here. It is based on a master-slave architecture. So we have the coordinator node at the top that has two main components. It has the HDFS name node, which is the component that is responsible for knowing where data live, in which nodes. and gives that information to clients so that they can do read and write requests accordingly. And we have the resource manager that knows, receives processing tasks from the clients and then distributes them to the worker nodes. The worker nodes process these requests, and they also embed a data node component from HDFS that is responsible for actually storing the data for the files. Apache Spark has a fault tolerance feature where if one of the tasks fails because a worker node crashed, for example, it will identify that and migrate the task, repeat it in a different worker. It also has another interesting feature where it can identify where data live and what data a processing task needs, and then it selects to send that task to the worker node that has that data, if possible. This is a principle that is known as moving the computation near the data. And this allows it to achieve very high performance because it reduces significantly the data that are shared across the network. And the reason I'm saying it is because it is yet another form of reduction of sharing, because worker nodes can operate only on local data, and they don't have to share anything with other nodes, essentially. So if we think about all these systems and now zoom out, we can see how they can be used in a larger ecosystem of services, let's say. So this is what we're looking at here. We have two services, Service 1 and Service 2, that receive requests from clients, and they also exchange data through an event log. And we have a third service at the bottom that receives events from this event log, stores them in a distributed file system, and periodically does some kind of data analytics. And you probably have noticed that I've colored some parts of this slide with a yellow color, and these correspond to the parts of the system that are involved in the processing of a single data item. So, for example, of a single user request. And I've done it mostly so that I can help you, I hopefully get some intuition of why we get increased performance and fault tolerance. Because you can see here that only small parts of every bit of this overall system is colored, and the rest are just white, which means they're not involved. They're not impacted by failures or anything like that. And of course, everything in the software world comes with trade-offs, and it would be reckless to only look at the positives. So here we'll have a quick look at the negatives, and we'll close with this. So the first pitfall of shared nothing architectures is complexity, and it has two phases. It can be implementation complexity if you're building a distributed data store yourself, for example, because you have to build all this stuff yourself, like replication strategies, partitioning algorithms, and consensus protocols. But even if you decide to use another one that is out there, you still have to handle some form of operational complexity. Because of the distribution, these systems come with many different failure modes, and you have to be familiar with them and have mitigations in place. The second pitfall I've talked about already is reduced flexibility in some cases. First of all, many of those systems provide a restrictive programming model. For example, I said a lot of the data stores provide purely key value access. And this means that you might not be able to change the data model of an application after the fact, or it might be very costly to do that. Stathis also mentioned the concept of hotkeys and how hard it is to change them. So you need to be very careful in choosing your partitioning strategy. And this can be a deal breaker if you're, example, a startup and you're trying to iterate fast and change the product depending on the customer feedback. The second area of reduced flexibility is weaker guarantees. So a lot of these systems provide weaker guarantees, like a lot of distributed data stores provide eventual consistency instead of strong consistency. And as we saw, Kafka, for example, that provides only ordering guarantees inside a single partition. And the last pitfall is the cost, the financial cost, which unfortunately a lot of us engineers neglect in many cases because we are attracted by the fanciest technology. And it's usually the business side that makes us think about it. Interestingly, the case for increased fault tolerance and high availability usually comes from the business side. So downtime has cost in terms of reputational damage or revenue loss. And in order to avoid that, we make our systems highly available. But if you look at the other side, making a system highly available also has its cost, because usually fault tolerance comes from introducing redundancy back to the system. For example, as we saw with replication, we have many servers storing the same data, so that if one of them fails, we can fail over to another one. But running more of these servers, of course, has a larger cost, a larger financial cost, right? So this is essentially a balance, a trade-off, and you have to strike the right balance there. And of course, it's not always straightforward. It's something that can be quite challenging. So this is everything I had to present today. At this link, you can find a blog post that I've written that goes into a bit more detail compared to what I could do in just 30 minutes. And also, I have written a book about distributed systems, and I've created a coupon for just this group of people today. So you can use this link to get a copy of the book with a 60% discount. And with that, I think we can move on to the Q&A part.
Hello, sorry. Thank you for the talk and also for the voucher at the end. Hope people will appreciate that. I'm gonna just read the questions that came through. Okay, question. Shall some common data be shared by multiple services? For example, the user service may be the owner of the user data or database, but user info, for example, username, I believe is the common data needed by many other services. Shall other services always ask user service for the usernames, ignoring caching for now, or tap into the user database directly?
Yeah, yeah, that's a good question. Unfortunately, I'm afraid it's one of those questions where you will get the common response, which is it depends, right? Like, of course, having a single service that is storing that has many benefits. If you want to, you mentioned caching there. Of course, if you want caching, you can do it there. You could also do caching on the client services as well. But it has other benefits as well. For example, think about, first of all, by not letting other applications access this database, you essentially sealed it in some way. It's, the property of encapsulation, information hiding, right? So it's typically useful to provide just a clean interface through which other applications can access user data. And it can let this team evolve the application better. If you let other people write into your database, imagine what happens when you want to add a new field, for example, and you want to do a migration, right? You don't have the sole control of the database. Other people are accessing it, so you have to coordinate. You need to have some coordination there to make sure it is done in a safe way. So that's one of the main propositions of microservices. You provide the data the way you want, and then you can you decide the interface of your application, how you do internal implementation changes without having to talk with your customers, essentially.
Cool, thanks. Billing service will need to access user and order data. Does it call user and order service? That creates dependency on those services and might slow down the billing service as well. guess it's a similar question to the one before.
Give me a second, sorry. Yeah, I think it's kind of similar indeed. So again, it's the same discussion, right? It's all about trade-offs, and it depends on the specific use case you have. If you are, let's say, a 5-person startup at this point, and you have 200 customers, you might not really care about that, right? If you are a larger company, you might care more about that. This dependency between the billing service and the user and order service, it can be seen both as a negative and as a positive as well, right? If you have large teams, if you're able to have large teams for every service, and they are capable of providing good SLAs, then it is a positive thing. You don't really care about the dependency. The teams are capable of providing the right service. If you don't have that, then this dependency can become a problem. Because having more dependencies means it might bring your availability down. So you might want to remove these dependencies. It's again, a case-by-case scenario mostly. There is not a silver bullet in these things.